In Chapter 3, we begin to take a look at the foundational probability concepts that are going to drive our inferential statistics in the second half of this course. So today we're going to work around the essential question of how are probabilities calculated. And we'll start with a foundation of probability, which begins with a little bit of vocabulary specific to probabilities. The first thing we need to know is that an experiment is a planned operation under controlled conditions. And then after running an experiment, we end up with these things that we call outcomes. An outcome is simply a result of an experiment. We can describe possible outcomes with what is called the sample space. And the sample space is simply a set of all possible outcomes. Often we're interested in describing what are called events. An event is some combination of outcomes. So to kind of give you an idea here how this plays out, let's say we flip a coin twice. That is our experiment. Our experiment is we are flipping a coin twice. An outcome might be a heads, then a tails. Those are results of the experiments. Our sample space would be either 2 heads, 2 tails, or 1 of each. The event then might be the event of getting both flips heads. It's a combination of the outcomes. Or both tails, or a heads then a tail. That's how that vocabulary works out. And that vocabulary we use as we calculate probabilities. And simply put, a probability is the long-term relative frequency of an event. And that probability is some value between 0 and 1. Usually expressed as a decimal. And for our course, even though the book doesn't always do this when it says it's going to, our course, we're going to round probabilities to 4 decimal places. That's going to be our general practice, 4 decimal places for our probabilities. And so if we want to know, if we say the probability of some event A is equal to 1, what we mean by that is we are 100% certain that it will always happen. The probability that the sun will come out tomorrow is 1. It will always happen. If the probability of some event A is 0, what we're saying is it will never happen. Probability that we will have class on Saturday is 0. It's never going to happen. Not this class. Not the class I'm teaching, at least. If the probability of some event A is 0.5, what we're saying is it's equally likely that it may happen or may not happen. Same probability of each. Basically, we have a 50% chance that it will happen. And then if that decimal is closer to 1, it's more likely to happen. If it's closer to 0, it's less likely to happen. And the whole idea behind calculating these probabilities is based on what we call the law of large numbers. And the idea behind the law of large number is as the repetitions increase, the observed, I'm out of space here, observed probability, the observed probability we call the empirical probability, will approach the calculated probability, or as we call it, the theoretical. If I flip a coin 10 times, the probability is half of the time I'll get heads. However, if I flip a coin 10 times, it is possible I might get 6 heads and 4 tails. The idea is as we approach a larger and larger number, we're going to get closer and closer to 50%. So if I flip it 1,000 times, it's going to be closer to 50%. If I flip it 1,000,000 times, it's going to be even closer to 50%. That's the law of large numbers. Now, as we're working with probabilities, we're often interested in what are called compound events, or several events happening together, or one affecting the probability of the other. So let's say, to set this up, let's just say event A means I reach into a hat and I draw out the number 1, 2, 3, 4, or 5. And event B means I reach in a hat and draw out the numbers 4, 5, 6, or 7. One way we talk about compound events is with the word OR. And the way we symbolize OR is we use a U for union, A union B, meaning A or B. We're saying either A, B, or both occur together. And I'm out of space, so we'll put it down here, together. So when we want A or B, either A or B, we have the number 1, 2, and 3 in A, 4 and 5 in both, and 6 and 7 in B. So when we say A or B, we end up with all of the numbers. Notice we don't repeat numbers that are in both. We just list them once, but A or B gives us all of those possibilities. Contrast that with AND. With AND, we flip the union symbol over, and we will say A and B, or technically that symbol means A intersect B. Means it has to occur in both A and B together. So the values that are in both A and B, you notice 4 appears in both, and 5 appears in both. I've heard it said that the difference between or and is the difference between an engaged man and a married man. An engaged man will buy his fiancée flowers and chocolates. He's on the pursuit. A married man, the wife is content if she gets flowers or chocolates. Both would be great, but at least he remembered something. Big difference, or and. We'll talk about where those come to play as we talk about conditional probability. And the way we write a conditional probability, you're going to see A, vertical line B. That's the probability of A given, that vertical line, we use the word given, the probability of A given that B has occurred. We have more information. What's the probability that I take an umbrella to work with me? Well, what's the probability I take an umbrella given it's raining outside right now? Now that I have that more information, now that I know it's raining, you'll probably say it's more likely I'll take the umbrella versus a random day it might be sunny. Why would I take an umbrella? That given information is going to change, probably increase that probability. The way we calculate the conditional probability, the probability of A given B has already occurred, is the probability of both of them happening, A and B, divided by the probability of the given information, the probability of B. So if I roll a die, we'll say a six-sided die, we'll always assume it's fair unless otherwise told. What is the probability that I get a 1 or a 2 given the roll was even? If you think about a six-sided die, you can get 1, 2, 3, 4, 5, 6. I want to know the probability that I get a 1 or a 2 given that I know the roll was even. So the evens are 2, 4, and 6. So the numerator is the probability that both happened. I got a 1 or a 2, and it was even. There's only one number, the number 2, out of 6 that satisfy that requirement. In the denominator, we'll put the probability of the given information. There are 3 evens out of 6. And I usually divide out the denominators. So we've got 1/3, or a probability of 0.3333. The probability that I get a 1 or a 2, given the roll was even, is 0.3333. I want to notice how that's different if the probability of getting an even, given I rolled a 1 or a 2. Again, the numerator is asking for both to occur, an even and a 1 or a 2. Well, there's only one number that is even and a 1 or a 2. It's the number 2. So 1 out of 6 divided by the probability of the given information. A 1 or a 2, there are 2 of those out of 6. Again, the denominators will divide out, and we have a 0.5, or a 50% probability that we got an even given the roll was a 1 or a 2. So conditional probabilities is the probability that both happened divided by the probability of the given information. Conditional probabilities can help us determine if some events are what are called independent events. Independent events are one does not affect the other. For example, if I roll a die and I flip a coin, what I get when I roll a die has no impact at all on what I get when I flip the coin. Those are independent events. One does not affect the other. And the way we show things are independent. We either show or disprove, depending if I'm trying to show they're independent or dependent. Show or disprove one of the following. See what the probability of A given B is. If that's the same as the probability of A, then clearly B had no effect on A's occurrence. They're independent. You can flip it around and say, do we know the probability of B given A? Because if that's the probability of B, A had no effect on B's occurrence. Another way, which I use more often, is the probability of A and B occurring. The probability that both occur is the probability of the first times the probability of the second. If we multiply them together and it gives us that compound probability, then they are also independent. And we only have to prove one of these, whichever is more convenient. Now I want to be careful with independent events where we say one does not impact the other. Don't get those confused with what are called mutually exclusive events. Mutually exclusive events are where both cannot occur together. Essentially, the probability of A and B is equal to 0. An example of mutually exclusive would be I roll an even number and a 3. Those are mutually exclusive events. You can't roll an even that is also a 3 because the 3 is odd. They're mutually exclusive. The probability of both happening is 0. All right. That's all the background for the probability that we need. Now let's start talking about some probability formulas. We're ready to start doing some math. The first probability formula we're going to use is called the multiplication rule. The multiplication rule says the probability of A and B, the probability of both events happening, is the probability of the first event times the probability of the second event given the first event has already occurred. This is an important formula for us. The probability of two events happening is we multiply their probabilities given the first one already occurred. The addition rule. This is used for an OR. The probability of A or B is equal to the probability of A plus the probability of B. But the problem is we've counted the overlap, the parts that are in A and B, we've counted them twice. We counted them in A and we counted them in B. So we have to subtract that overlap out so it's only there once. The probability of A intersect B. This is another key formula that we should know. So, let's finally do some examples. Let's let the event M represent somebody taking a math class. And S is going to be that they are taking a science class. The probability a student takes a math class is 0.6, because everybody loves math, so most people take it. The probability someone takes a science class is 0.5. Not as many people take science. And the probability that someone takes math and science is 0.3. The question is, are they independent? Does taking a math class have any effect on a person taking a science class? Or does taking a science class have any effect over taking a math class? Well, one way we have to show that is we take the probability of a math class times the probability of a science class and see if that equals the probability that they do both. If it does, they're independent. So a math class was 0.6, a science class was 0.5, and both was 0.3. 0.6 times 0.5, sure enough, is 0.3. So our conclusion is, yes, these guys are independent. Taking a math class has no effect on taking a science class. Let's do another one of these. Let's say L equals a person having long hair. And let's say F represents a female person. If the probability they have long hair, given they're a female, is 0.75, or 3/4 of the women have long hair, and the probability that the population in general has long hair is 0.5, are they independent? One way to know we're independent is the given probability is equal to the probability of just the front part. But here the given probability, L given F, is 0.75, and the probability of L is 0.5. Those two are not equal, so we say they are not independent. It seems there is some effect on long hair based on if you're a male or a female. It seems to be affected. Maybe not directly, but at least indirectly there's a relationship there. They are not independent. Let's try another example. Let's say Carlos makes 65% of his goals. If he makes his first goal, the probability of the second jumps to 90%. What is the probability he makes both? So what we're asking is, what is the probability he makes the first shot and he makes the second shot? Remember, an AND probability is the probability of the first times the probability of the second given the first has already occurred. Well, the probability he makes the first shot is 0.65. The second shot jumps to 90% if he makes his goal. So the second shot is 0.9 given the first shot went in. So now we have 0.65 times 0.9, and our calculator tells us that probability is 0.585, that he's going to make 2 shots in a row. How about we adjust it and say, what is the probability he makes at least 1 shot? So we're asking, what is the probability he makes the first shot or union the second shot? Remember, the probability of making a shot, or making an or, sorry, is the probability of the first part plus the probability of the second part minus the probability of both together, F and S. So the first shot, that's 0.65. Plus the second shot, it doesn't matter if he made the first one or not now. Carlos makes 65% of his goals. So the second shot's also going to be 0.65 because he makes 65% of all of his goals. The 90% is just given he made the first one. Then we have to subtract off the probability he makes both of them, which is 0.585. And so on my calculator, 0.65 plus 0.65 minus 0.585, the probability he makes at least one shot is 0.715. All right, so that wraps up some examples, just straight calculating probabilities. I want to look at, though, how we can calculate probabilities off of this thing called a contingency table. And a contingency table is just a table of frequencies and totals. There's a lot of talk about texting while driving leading to more dangerous driving behavior. So we're going to look at how the number of people who text while they're driving and who don't text while they're driving, and compare that to whether or not they get a speeding ticket or if they get no speeding ticket. And with these contingency tables, there's always a total column and a total row. So we do a survey, and we find out there are 25 texters who speed, 45 non-texters who speed, for a total of 70. 280 texters who don't get speeding tickets, 405 non-texters who don't get speeding tickets, and 685 non-speeding tickets total. And so if you add up those rows, we get 305, 450, and 755. So you can see there's a total of 755 people in this study. What is the probability we have somebody who does no texting? So no texting. This is all of the non-texters. So we're going to grab 450 out of the total 755. So 450 out of 755, the probability a random person is not texting is 0.5960. So that's kind of basic. How about this one? What's the probability that they get no speeding ticket and they're texting? No speeding and texting. Here we want both of them to occur. So now I look at the no speed column and the texting row. Both of them occur. There's 280 out of the 755 total that meet that requirement. So 280 out of 755, the probability there is 0.3709. How about the probability that someone is texting or they got a ticket? Texting or ticket. Well, when we look at our texters, there's 305 texters. Plus, when we look at our tickets, our speeding ticket, we have 70 people with a speeding ticket. But remember, with OR, we have to subtract off the overlap, because those 25 texting speeders got counted twice. So we subtract them off once. And then we can divide by the 755 total. So on my calculator, 305 plus 70 minus 25, hit enter, is 350. Divided by 755, we got 0.4636. How about this problem? The probability that someone is texting given they got a speeding ticket. Let's erase off all this orange stuff that's in the way. Texting given they got a speeding ticket. Given, we do the probability of both divided by the probability of the given information. So the probability of both texting and tickets, that's 25. Out of the given information. Actually, it should be 25 out of 755, but that's going to divide out here in a minute. The probability of the given information, the probability of a ticket, the speeding ticket is, ooh, what happened to my number there? Should have been 70. What happened to my 70? 70. There are 70 tickets. 70 out of 755. And you'll notice the 755s divide out. So we're left with 25 out of 70. The probability someone's texting given they got a ticket is 0.3571. Let's flip that around. Let's find the probability they got a ticket given they were texting. Now we still have a lot of the same information. We want both of them, the ticket texters. Ah, my number disappeared again, 35. The ticket texters is 35 still. Or it's 25, sorry, 25. Change the number, that'll change things. So 25 out of 755 divided by the probability of the given information, the probability of texting. Texting is over here, and I've got a problem with erasing too fast, I think. I had a total of 305. Sorry about that. So there's 305 total texters out of 755, and again the denominators will divide out. So we're just left with 25 out of 305, which is 0.0820. So the probability you got a ticket given you were texting is 0.0820. And that's how our contingency tables work. We can pull the information we want, use our probability formulas, and answer the questions. Venn diagrams. Venn diagrams help us make a picture of solutions with overlapping areas. And we're just going to touch on these really quick, not spend a lot of time on them. But the idea is if I've got information like 40% of students belong to a club, and 50% of students work part-time, and 5% do both. And we might ask some probability questions. We're going to ask, what's the probability that you are in a club or you work part-time? Or what's the probability that you do neither the club nor part-time? What's going to help us visualize this is a Venn diagram, which is a rectangular space with two overlapping circles, sometimes more, that represent the information. The first circle is going to be our club, and the second circle is going to be our working part-time. What's important is we have 5% who do both. So we've got 5% in the middle. On the left side, 40% belong to the club. But we've already got 5% of them accounted for. So there's 35% left that just do the club. Notice in the entire circle, including the overlap, you have 40%. Similarly, when we say 50% work part-time, we'll say 45 only work part-time because we have to subtract off the overlap of the 5%. So now we can say, what is the probability that you're in a club or you work? And because we've already done the subtracting and split it up, we can add up the pieces. 35 plus 5 plus 45. And we get 85%. 85% probability that they're going to do one or the other. We could ask, what's the probability that we do neither? Well, if 100% represents all of it, if we subtract 0.85, we get 0.15, or 15% do neither a club nor work part-time. So Venn diagrams can help us organize that information visually, if you like those. We're not going to spend a lot of time on those, but we are going to take a look at one last topic, and that is tree diagrams, which can help us visualize with a branch for each probability. Here's what I mean. Let's say I have an urn with 5 blue and 3 red marbles. You draw 2 marbles without replacement. It's going to be really difficult to calculate probabilities here by hand because the probabilities are going to change. If I pick a blue one on the first draw, then it changes the situation for the second draw. If I draw a red one on the first draw, it changes the situation differently for the second draw. So to help us organize, we're going to do a tree diagram where we draw a branch for the first draw. Where could I either draw a blue or a red? Now the probability of getting a blue marble on the first draw, there are 5 blue out of the 8 marbles total. The probability of drawing a red is that there are 3 reds out of the 8 marbles total. Then we can do another branch for the second draw. And it can go one of 2 ways off of each of these. I can get a blue or a red. Both times, actually, a blue or a red. But we have to think something has already occurred. We have some given information. The probabilities are going to change. On the top half, a blue marble was drawn first. which means there are only 4 marbles, blue marbles, left. And there are no longer 8, but 7 marbles total. Although if we want a red on the second draw, there are still 3 red marbles out of the 7 total. Similarly, on the bottom half, there's 1 fewer marble, 1 fewer red marble. So if I want a blue, there still are 5 blues left, but there's only 7 marbles to choose from. Or if we want to get a red the second time, there are now 2 reds left because 1 was drawn first out of the 7 marbles. And if we go down the track of these branches, we get all the possibilities. At the top, we've got the blue-blue combination. Underneath that, it would be a blue followed by a red marble. Beneath that would be a red marble followed by a blue marble. Beneath that, if you follow the branch down on the bottom, is a red marble followed by a red marble. And what's nice about these charts is the probabilities are easy to calculate because we multiply probabilities down the branch. This is an AND. We've already calculated the given probabilities. So on top, 5/8 times 4/7, the probability of blue-blue is 0.3571. Or 5/8 times 3/7. The probability of blue-red is 0.2679. Red-blue, 3/8 times 5/7 is also 0.2679. Doesn't always work that way, but that's kind of neat. 3/8 times 2/7, the probability of red-red is 0.1071. Now we've got all of our probabilities. We're ready to answer some problems. What is the probability that I get 1 blue and 1 red? Doesn't matter what order, but 1 blue and 1 red. Well, we see a blue and a red here and a blue and a red here. So we need to combine those probabilities together, 0.2679 plus 0.2679. When we add those together, you get 0.5358. What's the probability, though, I get a red and then a blue? Now I'm asking that they come in order, red, then blue. So I want the red first and the blue second. That is only this single branch, third from the top, of 0.2679. How about this one? What's the probability we get a red on the second, given we got a blue on the first? This one's tricky. It's a conditional probability. Blue on the first, so we're only going to look at the blue on the first has already occurred. We're only going up this top branch. That's already occurred. We want the probability that we got red on the second draw. Well, that probability is right here on the chart. There's a 3 out of 7 chance. Or as a decimal, 3 out of 7 would be 0.4286. But we could have also gotten that using our formula. Our formula says we want both to occur divided by the probability of the second. The probability that both occur, red then blue, we just found out was 0.2679, divided by the probability of blue on the first, which is 5/8. And if you put that in your calculator, you get 0.4286 as well. So tables are a nice way to organize our information and pull our probabilities out. In fact, tables make really easy what we call Bayes' theorem. Bayes' theorem is a way we can calculate conditional probabilities when we've got the backwards information. It's the way that we can calculate the probability of B given A when we only know the probability of A given B. We've got the wrong directional information. Bay came up with this great formula. It's the probability of A given B times the probability of B divided by the probability of A given B times the probability of B plus the probability of A given not B. We use a little apostrophe to represent not B, anything but B, times the probability of A or B not, of not B. And that formula is really not worth memorizing. Don't worry about it. That's the formula. We're going to solve it with a tree diagram. We're going to use a tree. We're going to circle the given information and mark the desired part. Here's what I mean by that. Let's say factory A makes 20% of my widgets at my store. Factory B makes 30%. And C makes the remaining 50%. The defective rate for each is 2%, 8%, and 3%, respectively. Respectively just means in the same order. So 2% is A's defective rate, 8% is B's defective rate, and 3% is C's defective rate. If a widget is positive, that's something we know, that's the given information. I'm not positive. So if a widget is defective, positive is example B, we'll get there. If a widget is defective, what is the probability it came from factory B? After all, factory B has an 8% defective rate, significantly higher than the rest. It probably came from there, right? Well, let's find out. If I can scroll right. So at the beginning, there's a chance it came from factory A, from factory B, or from factory C. Factory A made 20%, so its probability is 0.2. Factory B makes 30%, its probability is 0.3. And factory C, its probability is 0.5. Once we do that, we've got two options for each. It's either defective or it works. It's defective or it works. It's defective or it works. From A, the probability that we're defective is 0.02, 2%. Which means if we subtract from 1, the probability it works is 0.98. From B, the probability we're defective is 0.08. So subtracting from 1, 0.92 is the probability it works. From C, their defective rate is 0.03. Subtracting from 1, 0.97 is the probability that it works. I want to notice that each branch along the way, as we use Bayes' theorem, will add to 1. That's important. Now, in order to calculate the probability of any result, we multiply down the line. So 0.2 times 0.02 is 0.004. 0.2 times 0.98 is 0.196. 0.3 times 0.08 is 0.024. 0.3 times 0.92 is 0.276. 0.5 times 0.03 is 0.015, and 0.5 times 0.97 is 0.485. And if we add up all those orange numbers, we'll find out that all adds to 1 also. What we're going to do is we are going to circle the given information. The given information is that the widget is defective. So this 0.004, that's defective. This 0.024, that's defective. This 0.015, that's defective. We're going to mark what we're interested in, and what we're interested in is that it came from factory B. So factory B is what we are interested in. So it's a conditional probability. What is the probability it came from B given it was defective? The numerator is the probability of both. Notice both are clearly marked with an arrow and a circle. 0.024 divided by the probability of the given information. The defective. The defectives are all three green boxes. The 0.004 plus 0.024 plus 0.015. And you might want to do that on your calculator. 004 plus 0.024 plus 0.015. We end up with 0.043. So the numerator 024 divided by 043, the probability is 0.5581. About a 56% probability that if we have a defective part, it came from factory B. That's Bayes' theorem. We didn't have the B given defective. We had the defective given B, but not the B given defective. So we used the table, the tree diagram, to help us. This next example is one of my favorite examples of how Bayes' theorem becomes important. A lot of nurses take this class, and then what you'll find as a nurse is you have to explain things to patients because doctors are really bad at it. When you explain a positive result to a patient, if a patient gets a positive test result, does that mean they have the disease? Let's look at a real example of this working out. Let's say, according to Google, so it must be true, 0.35% of Americans have HIV. A test for HIV will give a false negative. False negative means it says, no, you don't have the disease, but you actually do. A false negative 0.2% of the time. And a false positive is when the test says, yes, you have the disease, but you really don't. No test is perfect, right? Those of you who have taken pregnancy tests know how that is. False positive, false negative. Am I really pregnant? If you get and it gets a false positive 1% of the time. And this is typical for tests. If you compare the consequences of a false negative and a false positive, the consequence of a false negative, where we say that you don't have the disease when you really do, is you will probably die because you won't seek treatment. You don't think you have the disease. The consequence of a false positive is that you probably get more testing and find out you don't actually have the disease. And you were scared for a while, which sucks, but you didn't die. So when they're designing a test, they have to decide how sensitive to make the test. They have to make the test slightly more sensitive in one direction, and they've decided we want to make the test more sensitive in the direction that saves lives. So false negative is usually much less likely than a false positive. Let's say you get a positive test. That's the given information. You get a positive test. What is the probability you have HIV? So the first decision has to split the world into two groups. The two groups that we have are 0.35% of Americans have HIV. The rest are healthy. So 0.35% as a decimal, that's 0.0035. The healthy ones, that's 0.9965. 99.65% of Americans are healthy, at least in terms of HIV. Then you take a test. You're either going to get a positive or a negative test result. A positive or a negative test result. A false negative is 0.2%. False negative means you really have the disease. You really have the disease, but you got a negative test. It should have been positive. So that probability of a false negative is 0.002, 0.2%, which means the probability you get an actual positive is 998. The false positive is when you don't have the disease. You're healthy, but it gave you that false positive idea. That probability is 1% or 0.01, which means if you're healthy, it'll say you're healthy 99% of the time. So where we get that the test is 99% accurate. So if we multiply 0.0035 times 0.998, multiplying to get our final probabilities, HIV positive is 0.003493. 0.0035 times 0.002 is 0.000007. And 0.9965 times 0.01 is 0.009965. 0.9965 times 0.99 is the everybody else, 0.98653. We're going to circle the given information. You got a positive test. The positive test is here and here. Positive test. We want to know what we're interested in, the probability that you have HIV. And that having HIV is only up here in the numerator. We're looking for the probability that you have HIV given a positive test. So the numerator is the probability of both, the 0.03493, divided by the probability of the given information. Those are the blue circles, 0.03493 plus the 0.009965. 0.003493 plus 0.009965. That denominator is now 0.013458. So now we've got 0.003493 divided by 0.013458, and the probability is 0.2595. So you get a positive test. What's the probability you actually have the disease? Only about 25%. Now granted, before you got the positive test, we said it was 0.35%. So it's gone up a lot, from 0.35 to 25. But it doesn't necessarily mean you have the disease. We need further testing to confirm that. And the further testing is usually a bit more invasive, and so we try and put it off until we get this first positive test. So that's Bayes' theorem. That's the basics of probability that are going to drive everything we're going to see in our inferential statistics. Start working on the homework assignment. In class, we'll start working on the practice assignments, and I'll look forward to answering your questions and continuing to work on them.